In this lecture, we'll continue looking at WFST algorithms. So first, a quick recap from the last lecture on weighted paths in WFST. You can skip this and go directly to composition if you're comfortable with the material we covered in the last lecture. So we discussed this idea of associating semi-rings with the weights of an FST. So in the WFST, you have states, you have transitions between states. On each transition, you have an input symbol followed by an output symbol, and they are separated by a colon. And then you have a forward slash followed by a weight, which or a score associated with each transition. So now, if I want to compute the weight of a path in this WFST, where a path is a sequence of transitions from the start state to any of the final states. Okay, how do I compute the path weight? So the first question that you need to ask is that what is the semi-ring associated with the weights in this particular WFST? Okay, so now semi-rings are associated with two operations, the sum operation and the times operation. Okay, and these can change and be different operators, and this will change the semantics of how the weights are accumulated. Okay, so if you're working with the real semi-ring, then the sum operation is just the plus operator, and the product operation is just your standard times operator. Okay. But if you're working with, say, the tropical semi-ring, then the plus operation is the min operator, and the times operation is the plus operator. Okay. So we will be using the tropical semi-ring for all the WFSTs that we deal with in this course. And I mean, unless mentioned otherwise, you can just assume that we're working with the tropical semi-ring. So now we'll come to the definition of the path weight. When you have X as input, the input string, and on consuming X, you're going to produce Y as the output string. Okay, so how do I compute the weight associated with this tuple XY? It's the plus operator applied to every path, which I'm denoting here by pi, such that X is the input string and Y is the output string. And I'm going to sum over, here sum is the semi-ring sum. I'm going to sum over the weights of all these paths. Okay. And what is the weight of a path? The weight of a path is the times operator applied to the weights of each of the individual transitions in the path. So the weight of the path pi is the times operator applied to the weights of every edge or transition E belonging to pi. Okay, so if we are looking at the tropical semi-ring, then I'm looking for the minimum scoring path, okay, among all successful paths which correspond to the input string X and produces the output string Y. And the weight of a path is just the sum of the weights of all the transitions in the path. Okay. So, right, so T of XY in the tropical semi-ring, it would be associated with the single path, okay, in the set of all successful paths corresponding to XY. And so this would reduce to the shortest path problem. So finding the shortest path, the minimum score weight path corresponding to the tuple XY. Okay, so this is a quick recap. Now let's jump right into the first WFST algorithm, which we'll cover in this lecture. It's arguably the most important algorithm, and this is called composition. So in composition, you're dealing with two WFSTs. Okay, let's call them T1 and T2. Say that T1 maps some string, input string X to a string Z, and T2 transduces the Z, the string Z, to an output string Y. Okay, then T1 composed with T2, where composition is denoted by this circle operator. T1 composed by T2 is a new machine that will have a single path that transduces the input string X directly to the output string Y. Okay, so it's kind of bypassing this intermediate string. So hope this the semantics is clear. So here, if I have, so going back, if I had two machines, okay, here T1 and T2, I have an input string alpha, beta, gamma, which is um, transduced to the output string small abc. And T2 takes the small abc as input and then produces capital ABC. Then the composed machine, okay, would be one machine which takes alpha, beta, gamma as the input string and directly produces capital ABC as the output string. Okay. So what is the kind of algebraic definition of composition? So here is the expression for the weight which is associated with an XY pair in the composed machine T1 composed with T2. It's the sum over all such Zs, okay, such that the input string X is transduced to the output string Z in T1, okay, and then T2 takes the string Z and then produces Y as its output. Okay, and you take the product of these two parts. So, and then so here in this tropical semi-ring, this would mean you're going to find the sum of the paths across all valid Zs such that X produces Z as its output from T1 and then T2 produces Y as its output on taking Z as an input. Take the sum of all such paths and you find the minimum scoring path across all of these paths. Okay, so that's implemented using the plus operator over all the Zs. Okay, so this is the composition rule. This is the algebraic rule which defines composition. Okay, so now how do we how can we think about constructing this composed machine? Okay, so let's start with have a working example. So this is a first machine M1 and this is your second machine M2 and you're going to try and compose M1 with M2. So you might have already deduced from the algebraic rule in the previous slide that the output alphabet of M1 needs to be consistent with the input alphabet of M2, right? Because strings that are produced as output by M1 are going to be consumed by M2 to then produce some other output strings. Okay, so there needs to be some, so the alphabets of the output alphabet of M1 needs to speak to the input alphabet of M2. Okay, so there needs to be some consistency there. All right, so how do we go about constructing the composed machine, M1 composed with M2? So you first build this, the state space, which is just all tuples where in each tuple you have under a Q and Q prime, where Q is a state in M1 and Q prime is a state in M2. Okay, so if you want to list all the possible tuples, you'll have 9 of them, okay, which we are listing here. And now you can, let's kind of step through each possible transition in M1 and the corresponding transition in M2 and look at what the resulting transition would be in M1 composed with M2. Okay, so this is the start state, which is denoted by this blue arrow. And here now you would set these to be final states, okay? Because these are final states in the individual component machines M1 and M2. All right. So now let's look at this first transition. So here, alpha is your input symbol, and then you have A, which is produced as an output symbol by M1. Okay, and this A will then be consumed by this transition, and you'll produce capital A as the output. So what would the resulting transition look like in the composed machine? It would look something like this, where you have alpha as the input symbol, and you're producing capital A as the output symbol. Right? So maybe let me talk. So if I define each transition, say E, okay, as coming from some large set of transitions, and the set of transitions I can define as, say, this is the set of states, okay? Then you have an input alphabet with epsilon. You have an output alphabet delta also with epsilon. And then you have a weight associated with each transition, which is a real valued number. And then you have an end state. So you have a start state, you have an input symbol, which comes from an input alphabet, an output symbol, which comes from an output alphabet, a weight associated with the transition, and an end state. So this completely defines a transition, right? So if for now, let me assume that all the input and output symbols in my machines M1 and M2 are non-epsilon symbols. Okay, we'll come to epsilon symbols in just a bit. So let's start with the simpler setting where we're only dealing with non-epsilon symbols. Okay, so then if you want to compute a transition in M1 composed with M2, okay, just based on transitions of M1 and M2. So say that you have a transition which is as follows, say Q1 X comma Y comma W1 comma Q1 prime. Okay, this is the transition in M1. And then you have another transition which will be look similar. So you have Q2, which takes Y as input, and then you have Z, some weight W2, and then you have Q2 prime. Okay, what would be the transition, the resulting transition in the composed machine M1 composed with M2? First, you would have a state which you can represent just as a tuple of the two states in the component machines. Your input will be X, your output will be Z. Okay, the weight will be W1 times W2. And the output state will be again a tuple, which you can represent as Q1 prime, comma Q2 prime. This is the resulting transition, right, in the composed machine M1 with M2. And this is exactly what this illustration is also showing, that if you have some Q1, and then here you have Q1 prime, right? So we are saying here you have some transition in M1 where X is the input, Y is the output, and W1 is the weight. And in M2, you have some Q2 transitioning into Q2 prime, where Y is your input, Z is your output, and W2 is the weight. Then the resulting transition in the machine M1 composed with M2 would look like Q1 comma Q2 transitioning into Q1 prime comma Q2 prime. Yes, and the transition would be X mapping to Z directly, and we have a weight, it would just be W1 times W2. Okay, in the tropical semiring, that would just be adding the two weights. And that's exactly what this alpha mapping to capital A is. You're going from Q1, Q2, which is denoted by this state, and then you're going directly to this state, which is the tuple, which is denoted by these two component states, okay, in M1 and M2. All right, so that's the first kind of transition. Similarly, you'll have, if you have alpha producing small a, and then you have the second transition here, which is small a consumed and then capital X produced as output, then that the resulting transition in the composed machine is here, right? So similarly, you can keep going, right? You'll keep deriving all these new transitions in the composed machine, and finally you're left with this set of transitions. Okay, you can do one additional pruning, which is that you remove all those transitions which you don't successfully reach from a start state. So that automatically removes this particular transition. So you remove that out, and this is the resulting composed machine that you're left with. Okay, so this was a simple example. Now things get more interesting when you have to handle epsilons. Okay, so this is when the machine M1 has output epsilon labels, or the machine M2 has input epsilon labels. Okay, that's when things get interesting, right? Okay, so say that now I'm just going to deal with these very simple two machines which just have a single transition, but this transition has an epsilon symbol as its output in M1 and an epsilon symbol as its input in M2. So what is the resulting transition that I would expect to see in my compost machine this kind of diagonal transition, right? Which takes which takes alpha as its input and produces capital A as its output, right? Okay. However, you could also have a transition as follows, which is that you are not moving at all in the M1 machine, okay? Because here, remember, you're consuming nothing, right? So you consume nothing, which means you don't move at all in the M1 machine, but then you transition and produce capital A, and so then you have this resulting transition in the compost machine, okay? So there's another way to think about this. You can imagine that there is this implicit epsilon epsilon self loop. So you can imagine these epsilon epsilon implicit self loops exist on every state, right, in every machine. This holds true for every state. So let's just to kind of easily think about how this transition appears in the compose machine. You can think of there being this implicit epsilon epsilon self loop, which means that here in this machine, you will take this epsilon epsilon self loop, which means you stay in this particular state. And then you're producing this epsilon as an output. Think of it almost like a regular symbol. And that epsilon is consumed in this particular machine. And then you produce A as an output, and that results in this transition, right? Similarly, you'll have these implicit self loops on epsilon self loops on every state. And so then you'll also have a transition that looks like this. Okay, so where you've taken this particular transition in M1, and then you've produced epsilon as an output, and then you consume that epsilon and still produce epsilon and stay in the same state. Okay, and so then you have this as your resulting transition in the compost machine. Okay, this is all fine. Okay, but now you can also have all these additional transitions which have now showed up in red, right? So you can have this transition because here you have this epsilon epsilon self loop, okay? And so then you stay in the same state, and then this epsilon is produced as an output, which is consumed here, and then you take this particular transition in the compost machine. Similarly, you can imagine having this transition, and then because of these, and then you'll have implicit self loops even on every state in your compost machine, right? Okay, so what is the problem? The problem is that this can lead to lots of duplicate paths, okay, or what is known as path multiplicity, okay. So the these duplicate or redundant paths, the problem is not just that unnecessarily you're blowing up the size of your machine, okay, and then your resulting computations with this machine are going to be very, very computationally expensive. So it's not just about the computational inconvenience, but it could also kind of violate the algebraic definition of composition, what we discussed in the very first slide about how the weights of paths are defined in a composed machine. That could be violated if you are operating with certain semi-rings, which are known as non-idempotent semi-rings. Okay, so this is a small technical detail, and you can skip over this if this is not so this is not crucial, okay, for you to understand. But for those who are interested, an idempotent semi-ring is one in which for every A which belongs to that semi-ring, it's said to be additively idempotent if A plus A is equal to A for all A. Okay, so this is the definition of an idempotent semi-ring, which is additively idempotent. And so non-idempotent, of course, this property is not satisfied. Okay, and if you have duplicate paths, then recall the composed paths. The weight is the sum over all z, right? And if you have all these redundant paths, and then say that there are some matching paths in the original transducers, which are counted some n number of times, where n is the number of redundant paths, okay, then you have all these additional counts, which should not have been accumulated in the composed part. Okay, so this could kind of really mess up the resulting weights in the composed machine. So how do we avoid this, right? So you want these duplicate paths to be filtered out or pruned out, and you want only the relevant paths to remain in the composed machine. Okay. So let's think about this very example, what we're looking at. So let's start with the following, which is that we're going to try and distinguish the epsilons. Okay, so what am I doing here? So I'm saying, let me say that the epsilon produced as output by the implicit self loops, I'm going to change them to epsilon ones. And then this epsilon, which is produced as the output in the non-self loop transitions, I'm going to change that epsilon to an epsilon 2. Okay. And similarly, the epsilon here, which is in the input of this transition, I'm going to change to epsilon 1. And on the self loops, the inputs, I'm going to change to epsilon 2. So here, immediately by doing this, all the epsilon self loops are eliminated, right, on my composed machine. So that's good. But the downside is that because of this particular mapping, I also lose out on this diagonal arc, because now this is producing epsilon 2 as its output, but I need epsilon 1 here to be consumed in machine M2. So here now let me refer to these slightly modified machines as M1 prime and M2 prime. Okay, so the modification is to the epsilon symbols. So now by composing M1 prime and M2 prime, I'm going to lose out on this diagonal arc, and that I certainly want. Right? That is kind of the main arc that I want to retain. So here's what I can do. I can introduce what I'll call a filter FST, and the role of the filter FST is actually to filter out all but the relevant transitions, okay, in the composed FST. So it turns out that this filtering operation in itself can be encoded as an FST. Okay, and then I can compose these three machines. So when I'm dealing with epsilon symbols, so M1 composed with M2, right? I can actually modify this as some M1 prime composed with a filter FST composed with M2 prime. Okay, and the resulting machine will be one in which all the redundant paths are eliminated or filtered out. Okay, so now we're going to try and motivate how this filter is designed. So here is one reason, what seems like a reasonable transition to add to my filter. So it's just a single state machine where I have just one state, which is the start state and the end state. So here I'm going to say let epsilon 2 map to epsilon 1. Okay, so that immediately helps me recover my diagonal transition, right? I also add these additional transitions. This I'm going to use as shorthand for epsilon 1 maps to itself. Okay, and A is a shorthand for any non-epsilon symbol. So A represents any non-epsilon symbol. Okay, so yeah, and this means that A is mapping to itself. This is shorthanding it. So here I have these self transitions, self loops, and epsilon 2 maps to epsilon 1. So now I've recovered back my diagonal transition, except I still have these problematic paths, the ones in red, ones which are highlighted in red. So what specifically are these problematic paths? How would I kind of make sense of them? Looking at the output from M1 prime, which is causing this problematic path. So the relevant output is this epsilon 1 followed by an epsilon 2 output from M1 prime. Okay, and similarly, an epsilon 2 input followed by an epsilon 1 input in M2 prime. This also causes a problematic path. So that causes this problematic path. This epsilon 1, epsilon 2 output from M1 prime causes this problematic path, right? So this is the problematic path. So I want to avoid these problematic paths. Okay. So how do I go about this? I'm going to now design my filter such that I prevent either of the two FSTs, M1 prime or M2 prime, from making what I'm calling these implicit moves, right? So those are these kind of self transitions followed by a real move. So here, what I want to avoid is this implicit move, which is epsilon producing epsilon 1, followed by a real move, which is consuming alpha and then producing epsilon 2. Similarly, here, what I want to avoid is this implicit move, which consumes epsilon 2, produces epsilon, and then followed by this real move, which is that it consumes epsilon 1, followed by capital A. So how do I design it? So here, this is the my state from before. Now, if I produce epsilon 1 as output, I'm going to move to a new state. Okay, and this new state, it does not accept any epsilon 2s at all. Okay, so it only accepts epsilon 1s. And the minute I see a non-epsilon symbol, I return back to the state. And here, once I produce epsilon 2, right, I never produce any epsilon 1s. So then I don't encourage this epsilon 2, epsilon 1, which is produced as an input to M2 prime. Okay, and then again, once I see a non-epsilon symbol, I return back to this particular center state. So this is my new filter now. Now, if I compose these three machines, okay, so it's a filter which explicitly doesn't take an input epsilon 1, epsilon 2, and it doesn't produce an output epsilon 2, epsilon 1. Then this is my resulting machine. Okay, so I have lots of these states. And so now every state in this composed machine is a tuple of three states, right? So state in machine M1 prime, a state in the filter, and a state in the machine M2 prime. So this is what the resulting state space would look like. And these are all the kind of transitions. If I prune away all the transitions which do not start which do not have a successful path starting from the start state, then I'm left with these three transitions. And this is exactly what I want to retake in my composed machine. Okay. So the filters, I mean, filters is an area, research paper or research area on its own. So there are many filters that one could design. This is one filter, okay, which works with composition. There are more efficient filters that have been designed in other papers. Okay, so I hope composition as an operation is clear. So let me kind of illustrate the power of composition with the help of like a simple game. Because this is the what is sometimes referred to as the telephone game, also called Chinese whisper. Okay, this is where someone whispers a message to somebody else, and then they in turn whisper what they heard to someone else, and so on. And finally, the last person in this particular cycle announces what he or she heard, and then it's fun to see how much it differs from what the original intended message was. Okay, that originated from A. So this could be stated as the following problem: given what D said, can you infer the message that A started with, right? So let's try and model this entire thing using FSTs. So say that the errors that are made by each player can be modeled using FSTs. So here, this is the message that D produced. And let's say that I'm going to represent this message as a phone sequence, okay, ransack pet shop. And each of so these are all error models associated with D, speaker D, C, and speaker B. And say that for now, these are all just simple single state machines. Okay, so this is shorthand for saying that if I see the phone B, I might kind of map it to R. And if I see R, I could, so there's also the identity mapping, which is I'll retain it as R. But B could also be confused with R. Okay. And similarly, let me build these error models, FST-based error models for each speaker. So now, if I combine all of these, if I compose all of these three error models, then this is the resulting error model. So this is the composed error model, which would just be a number of self-transitions which result from the composition of these three error models. Okay. So now, if I start with ransack pet shop, and I have this error model, which is the composed error model of all of these three speakers, B, C, and D. I'll take my ransack pet shop, which I can represent as an acceptor. So just this linear chain acceptor, right? I'll compose it with my, so let me go back. So I compose, and I'm going to compose it with my error model. Okay, so this will give me all possible transformations of this ransacked pet shop phone string, and all possible combinations that this could have been mapped into given this particular error model. Okay, that is what this composition will result in. But there's a small problem. I know that each of the messages which are produced by the speakers, they're going to be valid English words, right? They won't be nonsensical English words because there is a language model. So just composing the error model, this small error model with my ransack pet shop is going to result in all possible phone sequences, which could correspond, which will lead to invalid word sequences, right? I want to constrain it to be valid word sequences. So how would I do that? I can in turn compose each of these error models. So here I'm only looking at the error model corresponding to speaker D. I will left compose it with another FST, which tells me what are the valid words and what are the corresponding phone sequences for these valid words. So here you see that I have this machine which says that the word ban is this following sequence of phones, B followed by A followed by N. And the word ran is this particular sequence of phones, which is R followed by A followed by N, and so on. Okay, so I have this machine which tells me the phone sequences corresponding to all valid words. Now, if I compose this particular machine, so let me call this, say, L, and then here I have my error model, and then here I have L inverse. Okay, so here I've just inverted this particular machine, L. So if I start with L, so I have words, they are corresponding phone sequences. I have an error model, so it's going to modify all of these phone sequences with every error that was possible according to E. And then I'm going to map this back to valid words. Okay, so then it's going to eliminate all those specific phone sequences that do not correspond to a particular word. Okay, and I do this for, yeah, so this is L and L inverse. And then, of course, I also have to add a closure so that I can allow for a sequence of words, okay, not just a single word. And I do this for every single speaker. So just like I have this for speaker D, I'll similarly have 3 machines with the error model of speaker C. And similarly, I'll have another machine which incorporates the error model of speaker B. Okay, so now here's the entire pipeline. So I have an acceptor, which is corresponding to the decoded string from FD, which is ransack pet shop. So here now I'll call this a player model where I have a lexicon FSTL. I have an error model corresponding to the speaker D, and then I have the inverse, L inverse. And now I'm going to compose all of these machines put together. Okay, and then I want to find the best path in this resulting mega machine. And if I read off the input words on the arcs of this composed machine, and if I find the shortest path, okay, so let's assume the weights on all these machines are negative log probabilities, which means the shortest path would give me the most likely word sequence, okay, that this particular ransack pet shop could have mapped to. So if I read off the input words on the entire composed machine, and then that will be my most likely string that A is likely to have started with. I can also do additional things like I can try and find the best combination of paths in each player FST, okay, so that I can see how this actually transition, right? So how did Ransack Pet Shop become, yeah, so what's up? These were each of the intermediate paths that were traversed in the sequence of operations, composition operations. Okay, so this was just to show you that composition is very powerful in trying to compose simple machines to form really, really large and complex WFSTs. Okay, so let's do a quick recap of the composition algorithm. So if you have an FST T1, which transduces an input string X to Z, and then T2 transduces this string z to y, then the composed machine T1 composed with T2 transduces x to y. Okay, so the output alphabet of T1 is a proper subset of the input alphabet of T2, right? So if you have T1 with a specific functionality, so for example, say T1 removes punctuation symbols from a string which consists of uppercase letters, and then T2 comes in and changes uppercase letters to lowercase letters, then the effect that T1 composed with T2 has on an input string is to bring about both changes, which is it removes the punctuation symbols and it also lowercases the string. Okay, so that's kind of the overall effect of composition. Okay, now let's move on to two other very important algorithms, which is determinization and minimization. So we'll go over this in sequence. So WFSTs, they're constructed using various operations. Now we've already seen composition, which allows us to design these complex FSTs by combining simple FSTs. We also saw rational operations, which allow us to do the same. But the resulting FSTs, which are constructed as a result of these operations, they may have several redundancies. Okay, and if there are redundancies, such redundancies, it clearly affects the efficiency of operations which you will perform on these resulting WFSTs. So determinization, minimization are these optimization algorithms, which specifically are aimed at removing these redundancies. Okay, determinization could actually expand the size of a WFST, but in terms of time, it makes it much faster to process an input string. Okay, so we'll see what determinization means. And minimization, like the name suggests, it acts on a determinized machine and results in the smallest number of states, okay, with which you can represent a particular machine. All right, so in the rest of the slides, we will be talking about weighted finite state acceptors. And like we mentioned before, WFSTs you can think of as a special case of WFSAs by just interpreting the weight output label pairs as new weights, right, in an appropriately defined semi-ring. Okay, so then you can extend whatever algorithms we discuss here for WFSAs to the WFST setting. Okay, so first, when do we say that a finite state acceptor is deterministic? If one, that it has a unique start state, two, it has no two transitions emerging from a state which share the same label. Okay, so if you're at a particular state and you encounter a particular symbol, then there is only one other state that you can transition to. There are no options. Okay, and lastly, there are no epsilon labels. Okay, so epsilon labels always kind of add to the kind of number of choices that you can make, right, in your transitions. So there are strictly no epsilon labels in a deterministic machine. So what this is leading to is that any input sequence, when you traverse through this input sequence by consuming the input symbols, it yields a unique path in a deterministic machine. Okay, and this notion is very powerful because if you know that a particular FSA is deterministic, then there is only one unique path for an input sequence. And so then this would make processing an input sequence very quick because there are no choices. So here's a sample machine. So is it deterministic or non-deterministic? So you can very quickly say that it is non-deterministic because if you look at state one, on seeing the symbol B, you have two choices. So you could either go back to state 0 or you could transition to this state, which is say state 2. Okay, so this is a non-deterministic machine. Okay, so given mostly, I mean, typically when you're constructing finite state machines, it's easier to come up with non-deterministic machines, okay, which also involve epsilon labels. So here, at least for this example, let's consider there are no epsilon labels. So the determinization algorithm is to construct an equivalent deterministic finite state acceptor. Okay, so here's a non-deterministic
finite state acceptor or an NFA. And what you would like to construct is an equivalent deterministic finite state acceptor. So for any non-deterministic unweighted finite state machine, you can construct an equivalent deterministic finite state machine using a subset construction algorithm. Okay. So the main idea here is to think about merging together states in your non-deterministic machine by coming at it from the point of view of the input characters that are traversed. Okay, so if you're at a particular state, you're going to look at the transitions that you can make on a particular symbol. And if there are multiple such transitions, then you're going to consider all the states that you're going to reach based on the same symbol. And you're going to merge all of those states and make it a new state in this deterministic machine. Okay. And there is an additional step. So here, at least in this example, we don't have any epsilon transitions. But on such a merge state, you can do what is called an epsilon closure operation. So the epsilon closure you can consider to be a function which takes a state and returns a set of states that are reachable based on one or more epsilon transitions from any of the states in that set. Okay, so through this process, you keep constructing new states. And when you run out of new states to construct, it means that you've converged. Okay, then you have an equivalent deterministic machine. So let's do that for this particular example. So say we are starting from state 0. You have a transition out of state 0 on seeing the input, on seeing the symbol A, and that's the only transition that you have, right? Going from 0 to 1. So you retain that in your deterministic machine. Now from state 1, you only have transitions out when you see the symbol B, but it's the same symbol B. You can either transition to state 0 or 2. Okay, so now I'm going to construct a new state, which I'll label as 0, 2. And that is reached from 1 on the symbol B, right? Similarly, keep constructing. So you have this transition. And then from 0, 2, if you see the label C, then you transition to state 3. Okay, now from 0, 2, if you see this symbol A, from 0, if you see A, you transition to 1. And from 2, if you see A, you transition to 3. Okay, which means now you have a new a set of states, which is 1, 3. And this is reached from 0, 2 on seeing the symbol A. Okay, and on seeing B from 1, 3, you come back to 0, 2. And similarly, you also have the state 2, which is just retained, which you can reach from 3 on seeing symbol B, and then you can see symbol A and then return back to 3. Okay. So here, and one more thing to note here is that so the 0, 2 is marked as being a final state, as is state 2. So as long as any of the states in the set of states are final in the original non-deterministic machine, they will be a final state in the deterministic machine. Okay, so 0, 2 is final because 2 was a final state, and then 2, of course, stays as a final state. So this is our resulting machine. So now you'll see that when you reach state 1, there is no longer any non-determinism when you see the symbol B, right? You'll just transition to this new state when you see the symbol B. So this is the equivalent deterministic finite state acceptor. Okay, so this is all well and good, right? And I mentioned that for unweighted finite state acceptors, you can always construct an equivalent deterministic finite state acceptor. And the states correspond to subsets of states in the original finite state acceptor. Now, when you move to weighted finite state acceptors, it turns out that there are some weighted finite state acceptors which are not determinizable. Okay, so here's an example, an explicit example, which is a weighted finite state acceptor, and this is not determinizable. Okay, so this is a non-deterministic weighted finite state acceptor. So here, if you have a string of the type A, B, n times, and then followed by C, then the weight of that string is n. But if you have another string which is a, b followed b n times followed by d, then the weight of that string is 2n. Okay, because you can see that these two self loops have different weights. Okay, so here let's assume that there is a deterministic FSA, okay, which is equivalent to this particular machine. Now, after A and seeing B n times, suppose the FST incurs a weight n. Okay, then when you see C subsequently, that's okay. Okay, it'll accept it and it incurs 0 weight because of this particular transition, right? And now what happens when after seeing A and B n times, you encounter D? Okay, it has to incur an additional weight of n, right? Because the total path weight needs to be 2n. So it needs to incur an additional weight of n, except at this state, after having seen A and then B n times, the machine cannot remember n because it's a finite state machine and n is unbounded, right? So after seeing this A, B, n, the machine is not, it won't be able to remember n. So then how can it make this decision, right? So that's one way to intuit that this is a machine which is not determinizable. Okay, and so there is a more formal way to state this. I mean, as to when weighted finite state acceptors are not determinizable, and that's when they do not satisfy what is known as the twins property. Okay, so here these two states are referred to as twins because from the initial state, you reach one and states 1 and 2 with the same label A, and then they have self-loop transitions on these states again with the same label B, okay, except the weights on these self-loop transitions are different. Okay, and this violates the twins property, the fact that these weights are different. So if there is a violation of the twins property, then you can straight away say that this is a weighted finite state machine which is not determinizable. Okay. So again, these are details. It's not really critical that everyone should follow this, but for those who are interested, I've added some references, okay, that you can go through further. Okay, so how do you determinize a weighted FSA? You again employ very similar subset construction algorithm, except now you have to also keep track of the weights, right? And if you're operating in the tropical semi-ring, then from a particular state, if you see a particular symbol and then you reach a set of states, you also have now associated weights, but you only need to keep around the min weight, and then you have some residual weight which you again need to do some bookkeeping. Okay, and then keep around those residual weights. So there is some additional bookkeeping which you need to maintain to kind of keep track of the weights of the parts. And then here you can see that weights can also be assigned to the final state. Okay, so these, especially this kind of residual weights, can finally ply on the final states. So again, I won't go into details of the algorithm per se, but the references do have more of these details for those students who are interested. Okay, and an important kind of a notion is that two weighted finite state acceptors are said to be equivalent if they associate the same weight to each input string. Okay, so the entire weight which is associated with the input string has to be the same across two WFSAs which are said to be equivalent, but the way in which the weight is distributed across the string can be different. Okay, it's just that the overall weight which is associated with the input string has to be the same, but they can be distributed in different ways. So now let's move on to the last optimization algorithm in this lecture, which is the minimization algorithm. Okay, so this minimization is applied to an FSA which is already deterministic, And the goal is to find an equivalent deterministic FSA which has the least number of states and the least number of transitions among all the deterministic weighted automata which are equivalent to the FSA in question. Okay. Now, unweighted FSAs, they're known to have a unique minimal FSA. And there is kind of a standard minimization algorithm due to Hopcroft and Moore, which involves finding kind of equivalence clauses of states which could be merged together, okay, to in the minimized machine. So roughly, the algorithm works as follows. Two states of a deterministic FSA, they are said to be equivalent if there is no string that gives different outcomes when you start from the same state. Okay, so how you can start this algorithm off is that you write down a table of all the pairs of states. Okay, so let's maybe work this out for this particular example. So all the pairs of states, you'll have 0, 1, 0, 2, 0, 3, okay, 1, 2, 1, 3, and 2, 3. Right? These are all the pairs of states. Now, first thing you do is that you're going to mark. So you're going to consider a pair of states as being marked as distinct if one of these states belong to the set of final states and the other state belongs to the set of non-final states. Okay, so those would be 0, 3, 1, 3, and 2, 3, right? Because 3 is the only final state. So these are all pairs which we are going to mark, okay, because they consist of one state which is part of the set of accepting states and another state which is part of the set of rejecting states. And now you're going to keep repeating the following sequence of steps. So if you go through all the remaining unmarked pairs, okay, and so say that I'm going to consider one unmarked pair, say sum AB, and from that pair, I'm going to look at what is the state pair that I reach on a particular symbol, say A. Okay, so if I consider 0, 2, then from 0, I'm going to look at where I move to on seeing the symbol A. And from 0, you move to 1. And from 2, there is no transition with A, right? So assume that this doesn't exist. And so what you're going to look at is whether the resulting pair, pair of states that you reach, if it is already marked, okay, then you're going to mark this current unmarked pair that you are considering. Okay, and if it's I mean this kind of a situation where there is a transition out of one of these states, but there is not even a transition out of the other state, you can certainly mark those. Okay, so for example, from 0 you have a transition out with A, but from 2 you don't, so you can mark 0, 2. Similarly, if you look at 0, 1, from 0 you have a transition on A, the symbol A, but there is no transition out of 1 with A, so you can mark that as well. Now the only remaining unmarked pair is 1, 2, right? And if you look at 1, 2, on seeing D, from 1 you transition to 3, but from 2 also you transition to 3. Similarly, if you see E, from 1 you transition to 3, and from 2 also you transition to 3. But so it's not a marked pair of states, right, which you're going to reach on seeing any symbol from this state 1, 2. So this remains unmarked. And this is this kind of non-distinguishable pair of states. Okay, and so what this means is that 1, 2 are kind of equivalent, and so you can merge them in the minimized machine. So here you'll see 1, 2 is merged, and then you add the appropriate transitions from 0 to 1, 2 and 1, 2 to 3. So this is the resulting minimized machine. So this is roughly this is the minimization algorithm. So I'm not being very formal about this because you don't need to know exactly the details of the minimization algorithm, but it just suffice to know that there is a minimization algorithm which can be applied to unweighted FSAs, and then you're guaranteed to get a unique minimal FSA, okay, with the application of this algorithm. Okay, how do things change when you move to the weighted setting? Okay, so now you have a weighted deterministic FSA. How do I go about doing minimization, right? So one thing that you could do is that you just view the weighted deterministic FSA as an unweighted FSA by interpreting each pair AW, where A is like a symbol and W is the weight. You just interpret each of these pairs as a separate label, a new label, and then you just consider the entire resulting machine as like so just consider this to be like an unweighted FSA now that you have merged these pairs AW, okay, as a single label. But what happens here is that all of these get merged as distinct labels, okay, because every pair, even if you share the same label, if you have a different weight, it gets mapped to another different label. And so then applying the minimized standard unweighted minimization algorithm doesn't actually work. Okay, so it becomes necessary to do some kind of weight distribution to identify which states you can actually merge, okay, so that you end up with a minimized machine. So we already talked about what it means for two FSAs to be equivalent, weighted FSAs to be equivalent. So now when are two states said to be equivalent? So two states are equivalent if for every input string which starts from the two states, the outcome, which is the weight assigned to the string, right, from those particular states to a final state, will be exactly the same. Okay, so I'll say that again. So two states of a deterministic FSA, they're said to be equivalent if there is no string that will give different outcomes starting from that same state. Okay, so that is when the states are said to be equivalent. So you want to identify these equivalent states so that you can merge them and in your resulting minimized machine. And to be able to do this equivalent state identification, first you will need to redistribute the weights, okay, or it's also known as weight pushing. And we know that reweighting is okay, like we're not messing with the resulting machine. So it'll be okay as long as the resulting machine is equivalent. So remember from before, two weighted finite state acceptors are said to be equivalent if the input strings have the same weights in both machines. And the weights can be distributed in different ways. It's just that the input string has to have the same overall weight in both machines if they are equivalent. So you can do any kind of reweighting as long as the resulting reweighted machine is equivalent. So here's one algorithm which is known as weight pushing. Okay, weight pushing, the effect it has is that it normalizes the distribution of weights along the paths of a weighted automaton, and it does this by first imposing what we'll call a potential function on the states. Okay, and how does the potential function work? On each state, so for the initial state, the potential function is 0. So it just takes a value 0. And for every other state, it's the cost of the shortest path from that particular state to a final state. Okay, that's the potential function. So from here, the shortest path has a weight of 2. So that's the weight assigned to 1. From state 2, the shortest path has a weight of 1. So that's the potential function associated with 2. And from state 3, of course, it's just 0, right? Now, once you have this potential function on the states, you can assign these new weights to each transition, which would just be the potential function of the destination state minus the potential function of the start state, okay, for each transition. So here it'll be +2 for this arc. Here it'll be -2, okay, because it's 0 minus 2. Similarly, here are the kind of new weights that are associated with each transition, which are marked in green. And now the reweighting to all the transitions is going to be, you just, whatever these weights are in green, you just add that to the transition weights. So now the new weight for this particular transition becomes +2. The new weight for this particular transition becomes 0 because you started off with 2 and then now you have this -2. So you can see this reweighting. You can easily see that you've done this kind of redistributions such that the total weight assigned to a particular string stays the same. Okay, so earlier you had, if you look at this particular path, which is AD, it incurred a cost of 2. And similarly here you did a redistribution so that you're pushing the weights closer towards the start state of the machine. But the total weight of the string AD still stays 2, right? Okay, so now you've done this redistribution using this potential function where you're kind of moving the weights towards the start state. Once you've done such a weight pushing, now you can treat these label weight pairs as new labels. Okay, and then so you can kind of map them down to new labels, and then you can just simply apply the unweighted FSA minimization algorithm on top of this. So you will end up with something that looks, some machine that looks like this. Okay, so with the weight, so there are certain guarantees that come with weight pushing. You're guaranteed to end up with a minimal weighted finite state acceptor under some specific technical conditions which are required for weight pushing to be effective, right? And so the specific technical conditions, we're not going to go into details, but this is the general kind of setup when you have weighted finite state acceptors and you want to minimize these machines. Because you first do a weight pushing step such that you can identify equivalent states and merge them. So here, once you have done the weight pushing, these now emerge as equivalent states because you have exactly the same transition weight combinations, okay, out of 1 and 2, resulting in 3. All right, so with that, we'll end this particular module. And in the next module, we're going to look at how WFSTs are used exactly in speech recognition systems.